All right, so we've talked about the volume of cones, we've talked about the volume of prisms, we've talked about pyramids, we've talked about cylinders, and really the last topic for us to cover is the volume of a sphere, right? So if you think about a soccer ball, that's a sphere, a basketball, a baseball. Those are all spheres, and a sphere is just the three-dimensional version of a circle, right? If you took a circle, let's see, if you took a circle and you put it on a spit roast, right? And then you spun it around really fast, it would start to look like a sphere, okay? Um, and so what a sphere is just a three-dimensional version of a circle. So let's see how well I can draw a sphere. That's my best shot. Um, and so, just like we had a base in our pyramids and in our cylinders and in our prisms, spheres also sort of have a base, and it's slightly different because circles are a little bit interesting. Um, but it's the circle right in the middle of the sphere, right? So hopefully we can all agree that there's some center point in the circle, right? And if I take this center point out to the edge of the circle at any place, it should be equally far away from all those. And so each of these would be a radius. Okay, and so the radius has the same definition. We can just now go in any direction. Okay, really the definition of a sphere is all the points that are the same distance away from that center point. Okay, now we also, the important thing there is that from one side of the circle or one side of the sphere to the other side of the sphere through the center point, we have the diameter, okay, which is just 2 radius. Now, what that's called on a sphere is a great circle. Ooh, if I could spell it all. Great circle. Okay, and a great circle is the largest circle that can be drawn on a sphere. And the way that we know that it's the largest circle is because it goes through that center point, right? And so if it's going through that center point, then it's hitting the outsides of the circle at the widest points, and so that's what we call a great circle. And that great circle, the area of that great circle inside of the sphere is essentially what we would call our base, if you will, right? That's that red area there. So right here, let me do it in blue. Right here, this right here is a great circle, right? And it goes through this point. It's kind of tough to tell from this angle, but that point is part of the circle. Um, Something like this would not be a great circle, right? It's not the biggest possible circle. Um, it doesn't go through that middle point there, and that's still a circle, obviously, right? We could find the area of that circle if we had the radius, but it's not a great circle. And for what we want to do, we really want to focus on great circles because they allow us to find the volume and surface area of a sphere, right? So that being said, the only thing that we need to find the volume of a sphere is actually the radius, okay? And to find the volume of a sphere, our formula is 4/3 pi r cubed, okay? And now we could use calculus to derive this formula um, from just having a circle, and that's great. But the way that the formula was found in ancient Greece was they actually took a cylinder, which they knew how to find the volume of. Right? Took a cylinder, and they put a sphere in there that touched the top and the bottom. Right? And then they could tell they would like pour sand in, right? And so there's sand around the sphere. And because they knew the volume of the cylinder, right? they could compare that to the volume of the sphere, and they were able to come up with this formula, right? And now we can use modern mathematics to derive it in a variety of different ways. But truthfully, when the Greeks were discovering math, a lot of it was physical, right? The Pythagorean theorem came about of recognizing a pattern from something that they were already doing. Finding the volume of different objects came from using volumes of things that they already knew, and kind of playing around with displacement of water or displacement of sand, different things like that. And so math used to be very physical, and I think that's part of maybe what makes it difficult for people. But I guess enough of that side story, and we will try and find try an example, right? So example 1, we are going to find the volume of a soccer ball whose radius is 4.5 inches. All right, and once again, I'll try my best to draw well. And we will say that the radius 4.5 inches. All right, and I need to find my calculator. Where did I put that? There it is. All right. So I want to use my volume formula, which is volume equals 4/3 pi r cubed. All right, and so all we have to do is just plug in that radius. Okay, so I guess I probably should have made it a different color. We'll call it red. All right, so 4/3 pi, and it is volume, so we want to include those units. 4/5 inches cubed. All right, and so we're simplifying. 4.5, oopsies, not 45. 4.5 raised to the third power is 91.125 inches cubed. All right, and then we'd want to simplify more, so I'm going to combine that and the fraction, and if I do that, then 4/3 times 91.125 is equal to 121.5 pi, and we don't want to forget about the inches cubed, right? And so we've talked about exact answers. That happens when we have spheres. That would be our exact answer, but likely we're going to want to have 2 decimal places, and so 121.5 times pi is 381.70 inches cubed. Okay, so the volume of this soccer ball is 381.70 inches cubed. That's the amount of space that it takes up. Okay, and whether you believe the formula or not, that would be the way to go about finding the volume, at least based on what we know, right? And we have a variety of reasons to believe that formula. Okay, now that's pretty straightforward. You could be given the volume and asked to find the radius, right? You plug in the volume and then you're solving for the radius, and it's the same story where you're trying to just work backwards and solve for a variable. I don't believe there's one of those on the practice, but there may be. I can't remember for sure, right? Now, volume, not really a new concept. Surface area, I kind of skipped on the other shapes because it's pretty straightforward, and it wouldn't be that difficult to learn in a pinch. But the surface area of a sphere is slightly more difficult. Really not too bad, but it's at least worth covering so you have the idea in your head, right? So area is the space, like the two-dimensional space that something covers, right? So if I look at the area of a desk, I'm looking at the space that the top of the desk covers, not the volume, the depth, the height, all of that of the entire desk, right? So a piece of paper, we say it's 8.5 by 11, right? So if we multiply those together, we get the area of the face of the sheet of paper, but we never multiply by height to find the volume, right? And so the surface area is the area on the outside of the sphere, right? It doesn't take into account anything that's happening on the inside of the sphere. We just want to know, for example, if I were to paint my sphere, how much paint do I need, right? I need to cover this much area. Okay, do I need a gallon of paint? Do I need 2 gallons of paint? And so I'm just painting the outside of it, right? And so something that's pretty cool is that there's a calculus concept called the derivative, and if you take the derivative of the volume formula, then you get the surface area formula. And that's not something you guys really need to know, but I think it's a little bit interesting. And the surface area formula is 4 pi r squared. All right, so pretty similar. You just take derivative of volume and you get out the surface area. Okay, and so we've discussed that the surface area is what allows us to paint the outside of the sphere, right? Let's see how, maybe that's not great, but that's right. So we want to paint the outside of the sphere, so maybe we'll use green for surface area, okay? And so just like with volume, the only thing that we really need is the radius. And so let's use our previous example where we had a radius of 4.5 inches. I'm not going to redraw that picture, but hopefully that's okay with you guys. Example 2, got a radius of 4.5 inches, okay, and surface area is 4 pi r squared. I guess that should probably be an equal sign, right? And then we just plug in, not too bad. And thing to remember is we're looking at area, right? So we're squaring instead of cubing. It should be inches squared instead of inches cubed because we're looking at a surface. We're looking at an area. We're not looking at a volume that has depth and volume and that sort of thing, right? So once again, I'll simplify. 4.5 squared is 20.25. So 20.25 times 4 pi, and that's still in inches squared. And 20.25 times 4 will give us 81. 81 pi inches squared, and that would be our exact answer, okay? All right, we haven't multiplied out the pi yet, and if we were asked for a decimal answer, then we just multiply by pi, and we'll get out 254.47. So 254.47 inches squared is the surface area of our sphere, right? Or our soccer ball. So if you wanted to paint your soccer ball and you knew how much paint it took per square inch, then you could use however many inches are there to figure out how much paint you need, right? So if it's, I don't know, if you can cover 100 square inches with a gallon, then you need 2.5 gallons, right? And so that's kind of the value of surface area there. As the same with volume, if you're given a surface area, you could work backwards to find the radius. I believe there's a question on your homework where you're given the surface area, right? And then you've got to work backwards to solve for the radius, and then you use the radius to find the volume. Okay, and so it'll say, given a surface area, find the volume. Okay, and what it expects you to know is that you make this in-between step here. Okay. Beyond that, let me know if you have any questions. Hopefully this is not too bad. Actually, I'll write the formulas down here at the bottom, so if you want to have the video paused so you can look at the formulas while you work, that's great. I hope you guys are all doing well, and this may be the last time you hear from me. So if you do, I hope you guys all have a great summer, and I look forward to seeing you all in the fall.